In this session, the concept of hidden Markov model will be introduced to solve the problem of limitations of Markov model. In some cases, the Markov process is insufficient to describe the pattern we wish to discover. For example, sometimes the weather may not be observed intuitively, but folklore tells us that the state of seaweed is related to the weather in a certain probability. In this case, we have two sets of states: an observable state set, the state of seaweed, and a hidden state, weather condition. We hope to find an algorithm that can predict the weather based on the condition of the seaweed and Markov's assumptions. A more realistic example is speech recognition. The sound we hear is the result of interaction of the vocal cords, throat, and other articulators. These factors interact and jointly determine the sound of each word. The sound, observable state, detected by a speech recognition system, is produced by various physical changes in the human body, hidden state, extension of what a person really wants to express. Some speech recognition systems treat the internal pronunciation mechanism as a hidden sequence of states, and regard the final voice as a sequence of observable states that is very similar to the hidden states sequence. Such prediction or recognition task contains two kinds of states: observable state and hidden state, and cannot be described as a general Markov model. We can use hidden Markov model to solve the problem of decoding. As to the example of weather forecasting, we could find the most likely hidden state sequence, weather state, according to the observation sequence, state of the seaweed, based on HMM model. A hidden Markov model, HMM, is a statistical Markov model in which the system being modeled is assumed to be a Markov chain with unobserved hidden states. Its state cannot be directly observed, but it can be observed through the sequence of observation vectors. The mathematics behind HMM were developed by L. E. Baum and his co-workers. One of the first applications of HMM was speech recognition that began in the mid-1960s. Nowadays, many schemes of speech recognition use HMM. In the second half of 1980s, HMM began to apply to the analysis of biological sequences, especially DNA. Since then, HMM has gradually become an indispensable technology in the field of bioinformatics. In simpler Markov models, like a Markov chain, the state is directly visible to the observer, and therefore the state transition probabilities are the only parameters. In a hidden Markov model, the state is not directly visible or not certain, but the output, dependent on the state, is visible, which will be shown by the stochastic process of the observation sequence. Each state has a probability distribution over the possible output tokens. Therefore, the sequence of tokens generated by an HMM gives some information about the sequence of states. The adjective hidden refers to the state sequence through which the model passes, not to the parameters of the model. The model is still referred to as a hidden Markov model, even if these parameters are known exactly. An observed sequence of symbols is generated by starting at some initial state and moving probabilically from state to state until some terminal state is reached, emitting observable symbols from each state that is passed through. A sequence of states is a first-order Markov chain. This state sequence is hidden. Only the sequence of symbols that is emits being observable. Hence, the term hidden Markov model. Hidden Markov model is also a probability model about time series. The model has a hidden Markov chain to generate a hidden sequence of states. And then, through each state, a sequence of observations is generated. The figure shows a hidden Markov process, where S is the hidden state and Y is the observation. HMM is a double random process with two components. Markov chain describes the prior probability of each state and the transition of the state by the transition probability. General stochastic process describe the relationship between the state and the observation sequence by the probability of observation. The Markov process itself cannot be observed. It generates a state sequence that is hidden. Only the output observation sequence can be visible. In HMM, three parameters are important. Pi is the prior probability of each state. A is the state transition probabilities, which is also called transition matrix. B is the observation probability distribution for each state, which is also called the emission matrix. The basic HMM model includes 5 elements expressed as lambda equal n m pi a b, and can be simply expressed as lambda equal pi a b. N is the number of state. M is number of possible observation for each state. A is time-independent state transition probability matrix. B is the probability distribution of observations under a given state. Pi is the probability distribution of initial state space. For example, in speech recognition, N is the number of phones which are hidden states. M is the number of speech frames which can be analyzed to get a sequence of features. A stands for the probability from one phoneme to another. The figure shows a Markov process with unobservable and visible nodes, which is described by hidden Markov model. In speech recognition processing, a word is composed of several phonemes. Each HMM corresponds to a word or phoneme. A word is expressed as several states, and each state is expressed as a phoneme. In the figure, the hidden nodes X1, X2, X3 represent the states. The visible nodes 11, 12, 13, 14 represent the speech we hear or the timing signal we see. A is the state transition probabilities. B is the output or emission probabilities. The speech recognition task first specifies the structure of the HMM. When training HMM model, given n times series signals, Y1 until Yt, training samples, estimate the parameters, initial probability of n states, state transition probability A, and the output emission probability B. That's all for this session. See you next session.